So we're still here in lemma 1-2-14, and we are now working on proving part 2. So part 2 says that if you take a semi-algebra of sets on X and look at the algebra A that it generates, then you can actually write that algebra in this way, basically saying that all of the elements are not only finite unions of things in S, they can be written as finite unions of disjoint, pairwise disjoint things in S. So I'm going to put the full set up here. So let S be a semi-algebra of sets on X. Let A be the algebra of sets that it generates. So therefore, by part 1, we know that A is this set of finite unions of things in S. And so I've added this sentence. We will now show that every element of A is a finite union of pairwise disjoint sets in S. So we already know every element of A is a finite union of sets in S. Now we're going to show that we can get them to be pairwise disjoint. So I'm going to use induction. So we'll show that for any natural number n, that anything that you can write as a union of n things from S, you can write as a union of n disjoint things from S. And we'll try to do that for all n. Okay, so here it is spelled out. We will show by induction that for all natural numbers n, a union of n sets from S can be written as a union of n disjoint sets from S. Okay, so the first case is the n equals 1 case. That's trivial. Okay, so no need to even discuss that. A union, okay, I'm going to discuss it anyway. A union of one thing from S is already a union of one pairwise disjoint, collection of pairwise disjoint things from S, right? There's no pairs to check when you check pairwise disjointness if you just have one thing. Okay, so now suppose, so let me call this statement here star. Suppose star works for a given natural number n, we will show it works for n plus 1. Okay, so I need to prove star for n plus 1, assuming it works for n. So let's say we have a collection of n plus 1 things from S. So suppose, let's say S1 up through Sn, and then there's one more, Sn plus 1. These are all elements of S. Then what can I say about the union of all of these? So I'm going to display all n of them, and then there's this extra one that I'm adding on. Well, if you focus on these first n, then the union of these, by the induction hypothesis, can be written as the union of some pairwise disjoint things from S. So let me package them like this. This can be written as, let's say, S1 prime union up to S, and there might be more of them when we do this, or just a different number of them, Sm prime union Sn plus 1. So the number here might change, but that's fine. Can be written like this for some pairwise disjoint S1 prime through Sm prime. So basically this union can be rewritten as a disjoint union. Now pairwise disjointness requires that everything be disjoint from everything else, right? Any two things you pick should be disjoint from each other unless they're the same thing. So we have that among these, but then is this one disjoint from these guys? Not necessarily, right? So here's the picture in my head here. I know that, maybe there's S1 prime, S2 prime is disjoint from S1 prime, S3 prime is disjoint from S1 prime and S2 prime, but Sn plus 1, this guy sitting at the end, might creep in and take some points from here, maybe take some points from here, maybe take some points from here or not. So it doesn't have to be disjoint with each of them. So how do we fix this? Well, in this union, all of the points in Sn plus 1 sort of already account for the junk in here where it's creeping in. So I can just delete Sn plus 1 from each of these. So we have this union, this can be rewritten. So this is our original thing, right? Up here, our union of n plus 1 things. We've rewritten it like this, and we can further rewrite it like this. S1 prime delete Sn plus 1. And then union Sn plus 1. And proving that this is equal to this is like a pretty easy set theory exercise. You can do a set theory kind of Math 8 style proof that this is equal to this. And now again, this funky condition down here in the definition of a semi-algebra of sets, again, it gets to shine in this moment. So anytime you take yeah, I'm just realizing that, so we are taking complements here, but not in a situation where the thing being deleted, the A being deleted from the B, is actually a subset of the B, right? Here we're in a situation where this Sn plus 1 is being deleted is not necessarily a subset, but this is kind of annoying me. We don't really need, we don't need to say this here. We could, and it's just as powerful. But like, if A is not a subset of B, then you could always write B delete A as B delete A intersect B. And then A intersect B is a subset of B and would also be an S, since S is closed under intersection. So I think this definition would be equivalent if I just crossed this off. But I don't know, I guess if you want your definitions to be as weak as possible, so that it's easy to prove that things satisfy your definitions, then you would want to include this. Anyway, hopefully it's clear enough that you don't need to include this, considering that you have closure under intersections for semi-algebras. So include this or not, you get the same definition. So anyway, if you take a relative complement in S, then you get a finite union of disjoint sets in S. And now finally the word disjoint here in the definition matters. So going back to our proof here, each of these is a complement of things in S, all of the things showing up here. So each of these complements showing up is a union of disjoint things that are in S, of finitely many pairwise disjoint things that are in S. And let me just talk through the rest here. So since you have pairwise disjointness, okay, so in your mind, expand each of these as a union. Each of these is a union. This is a union. Each of these is a finite union of pairwise disjoint things. Now, since you have pairwise disjointness within these unions, and in the middle, you also have pairwise disjointness among all of the sets being unioned overall when you list them all together. And also, since this is disjoint from any one of these, it's also has to be disjoint from any of the building blocks that make up these as unions. So this will be disjoint from any subsets of these. All right, so I'm sort of avoiding writing out in the final step, but if you just expand these out in terms of a union of disjoint things in S, which is something we're guaranteed we can do by this third bullet point here, then overall here we have a finite, although possibly very long, disjoint union of things in S, which is what we needed, right? The goal was to show that, so this is equal to this, is equal to our original thing here, and the goal is to show that for the induction step, to show that this original thing can be written as a finite union of disjoint things in S. We have done that. All right, so back to the statement of the lemma. We've now proven 2. So I know there's a lot of set theory and it seems really basic, maybe not worth going through, but I do feel that it's worth going through carefully, mainly because you otherwise don't really appreciate all the different components of the definitions that we're getting. Like now you have seen where each bit here comes in, and it's only after you go through the proof of this lemma that you really understand the point of the semi-algebra of sets. Not after you look at the definition, right? Once you look at the definition, you're like, okay, why? But once you go through the proof of the lemma, then you're like, oh, that's why. Okay.